All right, thank you. Good morning, everyone. Welcome to CN Design 2 2021 final presentation. We are the Automated Parts Extraction and Cleaning for CNC, sponsored by Avid Corporation. The team members are Omar, Robert, John, Cord, Sean, Adarsh, and Reed. Now let's move on to the next slide. So this will be the agendas we will be following throughout the presentation. As you can see, the first one is project summary. So let's go to the project summary. So our sponsor is Avid Corporation. It is a machine shop currently located in Laramie, Wyoming. It is a manufacturing firm that deals with multiple CNC machines. So currently at Avid Corporation, after the parts are cut in the CNC machine, it gets dropped into a collection bin where the debris must be cleaned off manually. As you can see the picture on the right side, it's a machinist trying to clean the debris of a metal part using the air system. So this is what motivated us to create a machine that automates the process currently done by hand. By doing this, so we could free up an employee and allowing for higher production, which means it will increase the overall shop efficiency. Our machine will be able to handle variable metal sizes, and it has a short payback period. We will be talking more about payback period in continuous slides. So when it comes to contribution, we have it has contributed politically, globally, and socially, because 90% of the Avid clients are gun manufacturers. So that means the product that comes from the machine shop, it could be used for peace, creating a peace environment, or creating a secure system, and it also has an important role in human rights. The increased efficiency of the CNC process, our machine could be applied for other manufacturing fields such as medical equipment and the transportation industry with the increased safety of workplace. So far, there is no fully automated machine exists that has a portable or self-contained coolant and cleaning process for the horizontal CNC shows. So now I'll pass it on to Bobby to talk about the proposed solution.
So when we were talking about the client needs, we needed all these parts to be cleaned, and what we thought up was a machine where there would be a integrated wash bay system as well as an air system that would blow off all the parts, blow off all the debris, and then have it go off the end into a collection system. So you can see in the figure on the left, that's the configuration for small and medium parts. And in the picture on the right, that's the configuration for longer parts where the longer bars can be collected. So now when we start getting into the nitty-gritty of project goals and deliverables, we made a priority list from high, medium to low. And on the high category, there are the parts need to be cleaned of debris. It needs to be able to clean a variety of sizes since Avid cuts a variety of sizes of metal, as well as there needs to be a short payback period. In the medium category, we have that there needs to be no human intervention while the machine is in operation. We need it to have low maintenance and upkeep, a long life expectancy, as well as it needs to stack and organize the clean materials after they've gone through our washing system. In the low category, we also need our machine to contain all the cleaning fluid, as well as the machine needs to be semi-mobile. So now we'll move on to engineering approaches. I'll pass it off to John to talk about some of the engineering challenges that we encountered.
Thanks, Bobby. So looking at some of the specific challenges that this project faced, first, given the online delivery and policies throughout the year, it was absolutely critical to utilize a well-outlined work breakdown structure and Gantt chart is seen on the right here. In the top figure to ensure that deadlines were met and every group member always knew what tasks they were working on, just some good engineering project management skills throughout the year. As far as specific challenges presented with this machine, two of the largest challenges were the ability to handle the variety of metal stock sizes, which can be seen in this table on the bottom below, the classification of all the parts that Avid runs through their CNC saw. Our machine also needed to handle each one of these, as well as interweaving multiple systems, as Bobby briefly laid out. With each of these systems, they also provided challenges within themselves. For example, the structural system needed to provide adequate support for those medium and larger parts. The coolant system needed to provide sufficient flow to handle multiple nozzles. The air system, Avid expressed a large concern with not overtaxing their instrument air system for the rest of their CNC machines, so our machine was designed to not do that. as well as an integration of multiple circuits with the electronic system. So we'll get into each one of these systems now, starting with Sean and the structural system.
Thanks, John. So for our structural system, we decided to go with 10 series 80/20 extruded aluminum, largely for its great strength to weight ratio and also for the convenient T-slot design. We did a finite element analysis deflection simulation on the frame for our extended table, as this is the highest load-bearing part of our machine, and found a max deflection of 0.03 inches over the 49-inch span. We also did a stress analysis under the same conditions, which is a 100-pound distributed load, and ended up finding a factor of safety of about 5.8. So with these results, we were very confident with the capabilities of our machine and feel that it will withstand any conditions we put it under. So with that, I'll transfer to Court for the coolant system.
So some concepts from fluid dynamics definitely came in handy in this part of the project, specifically for the pump selection. It was determined pretty early on by our client that we wanted a very high flow rate of coolant in this part of the system, as opposed to a high pressure to forcefully blow the chips off. We wanted to instead coat the chips sufficiently with coolant and allow them to be have reduced surface tension and blown off later by the air knife. Looking at the figure in the bottom of the screen, the current prototype that we're running right now is using the 3 nozzle configuration, running just under 4 gallons per minute. This not only was our max flow that we were able to achieve, but it also allows for 3 different angles of contact on the parts and sufficiently coats them. Next, I will hand it over to Reed for the air system.
When looking at the air system, the design revolved around the requirement to be limited on the amount of flow we drew from the instrument air. We needed to determine the amount of air available in the shop so that we could select the right air knife size. So we used Bernoulli's to kind of model the instrument air system, and we got a flow rate that was available in the shop. In the upper right corner, you can see the flow rate available in the blue line and the flow rate required by a 6-inch air knife in the orange line. At our operating pressure of around 80 PSI, we are well below the amount available, which reduced the impact that we had on the instrument air. We got data from the manufacturer, ESE. As you can see in the bottom left-hand corner, the air consumption per inch in standard cubic feet per minute, but also important from the manufacturer is the sound level, which OSHA requires that a person working an 8-hour shift cannot be exposed to decibels of above 90 for more than 8 hours, and our air knife is below that at 72. So it's safe and efficient application of the air knife. So moving on to electrical, Bobby will get into that.
Thanks, Reed. So when we're looking at the electrical system, there's a few main instruments that I want to point out. So there's, in the green and purple, there's the coolant pump and the air solenoid. Those are kind of the main bread and butter of the electrical system, and all the other stuff is used to regulate those. As you can see, there's an Arduino which uses an ultrasonic sensor as the eyes to indicate when the coolant pump and air solenoid are turned on and off via the relays. You can also see in blue there's a preliminary switch which allows the entire electrical system to be shut off in the event that it needs to be turned off quickly. There's also a GFCI to prevent overloading. And in order to get power to the Arduino as well as the air solenoid, we needed a 12-volt power supply. So there's a little bit of everything in there. And so now I will pass it on to Sean to talk a bit more about the fabrication.
So the fabrication of our machine required us to build quite a few custom parts. The materials we selected for these were 16-gauge stainless steel for the drain pan and guide rails, 11-gauge mild steel for the extended table bed, and clear polycarbonate for the wash bay panels. The different equipment we used to make this happen was a bandsaw, a drill press, grinder and buffer wheel, a welder, and then some more advanced pieces of equipment, including a CNC press brake, a 3D printer, and a lot of water jetting. On the right side in the figure, you can see a few of the different custom pieces we had to make and how they were implemented into our machine. So with that, we can move on to some of the project outcomes. And first, I will pass it over to Court for the operation.
So here you can see a overhead view of our final project, and we'll just do a little run through starting on the left where the red arrow is, the parts are cut by the CNC saw and they leave there covered in coolant and debris, and they enter into our wash bay, the blue section on the picture, and that's where the 3 coolant nozzles constantly flow and coat the parts. From there, they get pushed into the green section where they are cleaned off by the air knife, and the air knife is run by the ultrasonic sensor that tells the air knife when to turn on and off based off their motion, and avoids overtaxing the shop's air system. And from there, they are deposited into the clean bucket. Next slide, please. So here is our fully functioning final products. On the left, you can see the configuration that was just shown in the previous slide for the parts less than 1 foot long. And on the right, you can see the extended table attachment. This allows for the 3 and 4 foot parts to load onto the extended table and be stored there. And both of these are implemented at Avid Corporation and working great.
Also, with our final project outcome, we created this PNID to show kind of the incorporation of multiple systems. Showing the instrumentation and piping is important to kind of keep in track of what was going on. This is something we're going to provide to Avid for their user manual, and something that will help them in the future should they need to replace a part or look at exactly what we put in there. So moving on, we're going to get into some product evaluation, determining how well our machine was able to meet the requirements set forth at the beginning of the semesters. So we ran some engineering tests. We wanted to determine how well our machine behaved, so we did a weight analysis of the chips removed. And then we also did a budget analysis to meet that low payback period. Some usability tests that we also performed were its ability to handle all size parts, minimum human intervention, low maintenance, it needed to deposit the clean material, and contain all the material and debris, as well as be semi-mobile. These are all tests that we ran in the shop. Kind of in this figure here also is a picture of some of the chips under Avid's microscope that they provided us. You can see they're really small on the scale of hundredths and thousandths of an inch. So they varied they varied a lot in their size, but were mostly, for the most part, pretty small. But moving on, John's going to give you some results from those tests.
Yeah, so looking at some of the critical testing results, it was essential to kind of do a weight analysis as well as a visual inspection was important as well. So looking first with our weight analysis of essentially the debris and the chips removed, we compared what our machine did to the performance of essentially a perfectly clean part, as well as comparing it to parts that have been cleaned off by a machinist by hand, kind of with the process that Adarsh introduced to you that Avid currently has implemented. So when compared to the parts that were perfectly cleaned, our machine was removing between 85 and 88% of debris and chips. And when compared to the current process that was used to clean them that Avid has been using with the machinist, our machine was removing between 95 and 98%. Also, visual analysis and inspection was completed by us, as well as with approval from Avid's machinist. You can see in the figure on the left, there's some cut material that is leaving the CNC saw covered in coolant and debris, and then travels through our machine, the process that Court outlined, and we are left with the clean product leaving our machine. So overall, these parts have all been tested and approved by Avid, and they gave them the go-ahead for use in a secondary milling or lathe machine, sort of to the required standards of removing that debris. So moving on to the next slide, we want to look at a budget reconciliation and analysis. The figure on the left here shows us the initially proposed budget that we presented to Avid last fall as a part of our design process. One thing to note there is the conveyor system was originally in our design plans last semester. We decided to remove this based on some design iterations that we went throughout the year. And overall, this freed up some budget space. But Avid was very happy with the $4,000 that we initially quoted them. The key number, where we stand now, the final prototype cost was just over $3,100. So with this, we can run a payback analysis that essentially takes the time to manually clean one bolt handle, as well as the estimated number of bolt handles that David was planning on producing in 2021, the average hourly wage of the machinist spraying them off, takes into account a few other factors, and we can get a total annual savings and then a payback period that our machine produces. So overall, this number is well under our 6-month goal that we had set, and David has been very happy with not only the budget, but the payback period. One other quick thing to note was the estimation of manpower resources that our group has delegated for this project, estimated over the past year. So, next slide, please, Bobby. So finally, we want to go back and look at where we stand now with all of the testing requirements. All of our requirements, most of our requirements did very well, and our client has been very pleased. There have been some debugging issues with the Arduino, basically moving it to a point where it does work and it did pass, but it's inefficient, and our group is not comfortable presenting it to Avid with how it works currently. So we're working on a few last debugging issues before we can pass this test. That's the one highlighted in red there, the no human intervention. Overall, the only other one, you can see the machine will have a long life expectancy. We left this as expected to pass just because in the design process, we put a focus on choosing quality parts that will last for a long time, but ultimately only time will tell with this requirement. So overall, this is where we stand with the testing requirements, and Avid has been very happy throughout the process. So with that, I'll move it on to Sean.
Thanks, John. So now we can get into the safety and some of the next steps. So the safety precautions that we had to keep in mind is proper PPE while operating our machine, which includes ear and eye protection. Next, our machine does have high voltage components, and so all the machinists are greatly encouraged to use caution whenever dealing with those. Our system does contain all of the overspray of the debris and coolant inside of the wash bay to avoid debris from flying out. On the picture in the right, you can see the debris getting caught in our screener tray, which will have to be emptied out every week or two. Next, there are pinch points between the parts as they are pushed through the wash bay, so the machinists need to be careful not to stick their fingers in there when parts are moving through. And lastly, we have a highly visible control switch for the electrical system in case they need to shut our machine down in a hurry. Next, I'll pass it on to Omar for the codes and standards.
Thanks, Sean. So here are the codes and standards that we found applicable and related to our project. The code relations can vary from noise level of the air knife, eye and face protection from the chips, maintaining dry environment where wash bay is sealed with flaps and silicone to prevent having any leakage in the floor. And lastly, the guidelines for electrical usage in machinery, where all the wires are insulated, isolated, secured, and all systems are grounded, and the main shut-off switch is present. Now, next, for the recommendations, these are recommendations and improvement we suggest for further work in our project and an idea for next year senior design. So first would be extending the covered part of the wash bay so the coolant and the air are both contained. Second would be a repeatable way to mark where the guide rails are supposed to sit for different parts. The third one would be a way to keep the coolant from leaking off our machine and flowing back into the when they cut more than one bar at a time. Lastly, would be a potential idea for next year senior design would be to make a system where the system can carry and load multiple bars and be able to push the bars to the CNC saw entrance instead of having the operator setting the bar for every operation, which is every 5 to 30 minutes manually. Having this system operate automatically for multiple operations throughout the day can save time for Avid. Next. So we would like to thank our sponsor, Avid, and the machine shop, Spencer and Gary, and the judges for their time. And of course, Professor Kuhn and Professor Notter for their guidance throughout these 2 semesters. And now we will be open for questions.
Okay, I'm going to take the opportunity to use the little emoticons for a virtual clap for our speakers because we can't do it as we normally do. And we'll open it up for questions from the judges. So does a particular judge want to jump in with a question?
Yeah, I've got a question for you guys. First off, nice job. Looks like a great project, and I like the ROI and budget calculation that you did. My question is around some of the control systems and the electrical side of it. And I know you said there's some challenges with the Arduino. I was just hoping to understand of why did you select an ultrasonic sensor, and then what does that controls loop look like in integrating that sensor, and how did that control the system?
So most definitely. So we decided to choose an ultrasonic sensor just because there's the way that the jaws move on the CNC machine, there's a very specific routine way that the bars are pulled in, and it acts kind of like a big plate moving forward and backwards, just up the ultrasonic sensor's alley. So that was mainly the reason. We also have a housing for the ultrasonic sensor and a wire loom that goes underneath the machine where it's protected to access the ultrasonic sensor. So we tried to make it as robust and durable as possible while also allowing it to mount on the machine. And since we are adapting to a pre-existing machine, it needed to be semi-adaptable. So that was another reason why we went with something like that.
Great, thank you.
This is Heidi. I have a question. You said, I believe one of your criteria was a long life. How would you guys define long life, and based on your design, how long do you expect it to be able to work in service?
So on our goals and objectives, we wanted it to last longer than 5 years. That would be extremely optimal, and we picked the highest quality products that we could to ensure that it would last that long. And I think with that, Avid would be very happy, and I think that we would be happy as well.
And another part of that is one of the limitations and one of the hard things about this design was being able to cut more than one part at a time. Because if we were limited to only cutting one bar at a time instead of the 2 or 3 that they currently do, you're going to have to activate that solenoid for our air knife 2 or 3 times as many times, and that could decrease the life of that solenoid by the same amount. So trying to have our project be able to be fed as much material at one time and handle it all just as well was another way that we tried to increase the life expectancy.
Great.
All right, this is Sean speaking. So a quick question. So first, very nice work. Just a quick question. I do believe that you probably tried different solutions before choosing that inclined guiding rail and then that converged shape, right? So do you have any, can you talk about any other alternative choices that you either thought about it or you even tried before you end up with this final design?
I think you were breaking up a little bit for the first part of that question. I didn't quite catch it all.
Yeah, so basically while this system works pretty well, right? Basically finished, you achieved the goal in terms of percentage of weight, cleaning. But for that final design, for that dealing with the longer bar, right? You have that inclined guiding rail to guide that bar into the other side and then drop to whatever container you have. So basically my question is, have you, before you end up with this final design, have you ever thought about other alternative design possibility or even tried some other solutions?
Definitely, we thought about some other options, and one of the really hard things about that was trying to design our machine in a way that could handle both the small parts and the long parts, because there were other ways that we could have designed it to handle either or, but the method that we chose ended up working very well just by having an extended table that you simply unfold and put in place if you're going to be cutting long bars. Also, it's important to note that they cut way more short parts than they do long bars, and so that table will be folded away and tucked away most of the time. But to answer your question, yes, we did think about some other options, but the one that we implemented was the one that we thought was going to work the best. And so far it has been working very well.
Cool, thank you.
Okay,